This is section 10.7, partial fractions. And knowing how to do this becomes really important in a certain type of integration in calculus. So we just talk about it here and then it comes back later. So we're going to start off by just reminding ourselves how to add two fractions together. And when we do that, we need to find a common denominator. When we look at our two denominators in this example that we have, we should notice that neither one of them can be factored any further. And because of that, the lowest common denominator is actually the two denominators multiplied together. So in order to add these two fractions, we need to give each one of them the denominator that they don't have. So what I mean by that is that the first fraction there with the denominator x minus 2 will need a numerator and denominator of 2x minus 3. Understand that what I'm doing to this fraction is simply multiplying it by 1. And because of that, I am not changing it fundamentally, and that's what allows me to do this. I do the same thing with the other fraction. I will need to give both numerator and denominator the denominator that it doesn't have, so x minus 2, and then to not change it, we multiply the top by that as well. And then we just combine, and it's going to create one fraction. So our adding them together is going to give us x minus 2 and 2x minus 3, and then in the numerator we will have 2x minus 3. So now I'm just distributing. Boop, boop. And then I'm going to do that here as well. So 2x minus 4. And just combining what we have there, I have 4x minus 7 over x minus 2, 2x minus 3. So that's the combination of those two fractions that we have. We're adding them together. Now, notice we have some more basic example. You know, the fractions on the left are more basic. They have no factoring in the denominator, and those are actually what's called partial fractions. So partial fractions in this case are what we have on the left-hand side. But what we have on the right-hand side, this is a rational expression there. You should notice that, polynomial on the top, polynomial on the bottom. And we can rewrite those rational expressions as the sum of those partial fractions. And the process is not surprisingly called partial fraction decomposition. So what you really want to understand is that these two things are equivalent. Whoa. They're equivalent. And sometimes it's helpful to take something that looks like this and rewrite it into something that looks like this, especially for this situation that we'll encounter in calculus. So our goal in this section is actually to go backwards from what we just did. We're going to take the rational expression and we're going to rewrite that as partial fractions using this partial fraction decomposition. So there's a few different situations, and the first few are the most common. But the first case you might see is simply that you have, let's say you have a polynomial q of x, and it can be factored. So in this case, a and b are constants, and none of the factors are repeated. What that means is when you have a rational expression, p of x over q of x, so notice that q of x is in the denominator, that rational expression is equal to some number, a1, over the first factor, plus some number, a2, over the second factor, plus, and so on and so forth for all the different factors in the denominator. Okay, so to just start that out and show an example of that case that we just saw, the idea here is, notice that the denominator of this rational expression can be factored. So if you can, take a moment, see if you can factor that trinomial. So it should have pretty basic factoring. There are not too many factors of 10. We do want a difference to be 3. So we'll want 5 and 3, 5 and 2, 5 and 2. And then, there we go. We want the 3 to be positive, so the larger number will be positive, the smaller number will be negative, or -2. So notice, we have now the factored form in the denominator. So coming back to this, we now have what we have in this form where q of x is factored. What this says is that this thing is equal to a1 over x minus 2 plus a2 over x plus 5. Now, typically, I don't actually need my parentheses there if you don't want them. I mean, there's no need for those parentheses. You can, you don't have to. I'll just be consistent and not write them. So notice we have a1 plus a2. To make our lives a little bit easier, just, to write a little bit less, typically instead of a1, a2, using all that all the time, it's more common for us to just say A and B. So the goal of what we're going to be doing today is to be finding out what is A and what is B. What are the two numbers that need to be in the numerators so that that left-hand side equals the right-hand side. And so that's what we're going to be doing today. And we'll start off with just a slightly different example. Same idea here. Same idea. Take a moment, see if you can factor your denominator. That's really the key piece, is factoring that denominator. So, a lot of factors of 12, but we want the difference to just be a minus 1. So we have this. Okay, so all we did here is factor the denominator, left-hand side equivalent to the right-hand side, no problem. What this thing says for case 1 is it tells us that negative 3x minus 23 over x minus 3, oh, I need x plus 3, excuse me, x plus 3, x minus 4 has to equal a over x plus 3 plus b over x minus 4. Okay. So the way that we do this, the way that we find out what this a and b are, is the following. First thing I'm going to do is, and actually I'll put that below, think about my spacing here, but the first thing we want to do is multiply both sides by that lowest common denominator, x plus 3, x minus 4. So we're going to take what we have above and we multiply both sides by x plus 3, x minus 4. The idea here is it's going to rid us of all of our fractions, and then we'll go from there. So notice that the left-hand side, when you multiply it by x plus 3, x minus 4, the whole denominator is gone. It simplifies to 1, and all you have is this. On the right-hand side, when you multiply both sides by x plus 3 times x minus 4, that goes to each expression there on the right-hand side. The x plus 3 simplify with the expression that has x plus 3 in the denominator, but you still have an x minus 4. So you have a times x minus 4. The b, the x minus 4 simplify, but you're still left with x plus 3. So now we have this. Now we have what you see here. So we're going to do that. I will also then distribute everything. You can take a moment and distribute what you see like this. So here's all of our terms, no more parentheses. Now, second step is key. We are going to combine like terms right side. So I have negative 3x minus 23. On the other side, I'll have ax. I'm going to put the bx next to it. So the things that are similar are going to be the values that have the variable, and then the values that are the constant. So minus 4a plus 3b, like this. Now, notice one thing we can also do, which will help us, if I factor out an x, I have a plus b. There isn't anything I can do over here, the minus 4a plus 3b, so I'm not going to worry about that. I'll just rewrite that. But here it is. Once I write this, what I want to understand is the left side needs to equal the right side. We have an equal sign. That tells us that negative 3, which is multiplied by x, has to equal a plus b. Because the only way to get negative 3x on one side and a plus b times x on the other side is if a plus b equals negative 3. What also has to be true is that negative 23, or minus 23, is going to need to be equal to negative 4a plus 3b. And that those things must be true. So now, what I'll write one more line, and then we'll go from there. So this tells us, like I just said, negative 3 has to equal a plus b, and minus 23, now a negative 23, negative 4a plus 3b. Now we take ourselves back to, technically one of the earlier sections we've already talked about. Now we have to solve the system. We're trying to find the a and the b that work. So now we can solve this system for a and b. So we have a plus b equals negative 3, and we have minus 4a plus 3b equals negative 23. And then we just follow, what we've done in the past here. If I multiply row 1, so row 1, row 2, so I'll take row 1, I'll multiply that by 4, and then I'll add row 2. You can be as specific as you want with this part, but that will give us 4a plus 4b equals negative 12, and then minus 4a plus 3b equals minus 23. So you can see that's going to give us 7b equals negative 35. So that tells us that b equals negative 5. So we get that b equals negative 5. And then a plus b has to equal negative 3. So a plus b has to equal negative 3. So that tells us that a equals 2. So just for spacing reasons, I'll go ahead and put it up in another color up at the top. What we have now shown is that our a is 2. So I have 2 over x plus 3 plus, and then our b, which is negative 5. So negative 5 over x minus 4. So now we've done the partial fraction decomposition to say that these things are all equivalent. What I have here is equivalent to what I have here is equivalent to what I have here. Again, the reason we do this is because that last example, the one that I have in blue, the last expression set that I have in blue, the sum of those two expressions is an easier way to deal with something that we do later on in calculus. And so that's why we have it. That's why you have this method, because at some point you're going to do something with that. You're just not going to do it yet. But that is the partial fraction decomposition for that. So it's done. So this is the answer, just so that you know. Got a lot happening here, but this is the answer. And again, we needed to find this A and this B in order to make that happen. Okay, now there's another example. You could have a situation where you have the same repeated factor in the denominator. So notice you might have ax plus b, and then you might have it again. So if you have it again, you need to do a linear factor and then a factor that is squared, all the way up to however many factors in the denominator you have, again with just that number, that constant at the top. Okay, the constant at the top. So let's take a look at one of these examples. Okay, so the idea here is, in order to find the partial fraction decomposition of this, we will have 3 fractions that will be added together. But based on that text box that we saw with case 2, our first denominator needs to be x plus 2. Our second denominator is not an x plus 2, it's an x plus 2 squared. And our third denominator is an x plus 2 cubed. That's the key. So in a situation where you have repeated linear factors, you need to create multiple denominators where, depending on how high you need to go, you include a factor with that degree. But it is still just A, B, and now we'll have C. And in general, the method is the same. It just, now we have 3 variables, A, B, and C, that we're trying to find. They're constants, but we are trying to find out what they are. So, okay, to start this, we can do what we did before. So we will multiply both sides by this x plus 2 cubed. So multiply by the lowest common denominator. The lowest common denominator here, we do need to have all 3 of them. Not surprisingly, on the left-hand side, that will not give us any denominator at all. Great. But on the right-hand side, notice we'll have a times x plus 2 squared. That's because if I multiply both sides by x plus 2 cubed, that's what we're doing here, only one of them simplifies in this first fraction that I have. In the second fraction, I will have 2 of them that simplify, which leaves me with 1 of them. And in the third one, all 3 of them simplify, and we just have this. So the method is the same. The second thing we're going to do is just, well, what we can actually do, I think might be better, is just to multiply out the right-hand side. So let's do that first. So notice we have just a c, we'll have bx plus 2b, and then we do have to multiply out that x plus 2 squared. So we will have, notice that this is x squared plus 4x plus 4. And you do want to get to the point where you can do that pretty quickly in your head, something like x plus 2 squared. And now we multiply it by a. So ax squared plus 4ax plus 4a plus bx plus 2b plus c. So we're just multiplying it all out. And then, just like we did before, we combine things that are alike on the right-hand side. But understand that when I say alike, I mean we have to think about what's in front of the x squared, what's in front of an x, and what constants we have. So that's what we're doing here. So when I write this, I only have ax squared. That's great. That's really helpful. But I have 4ax. I also have bx. Now, just in order to save space here because of the space that I have, I'll actually combine those and also factor out my x. So, oh, I have a shooting star that I just made on my page here. Okay. So, now I'll factor out the x with, I'm using this term. So So I'm dealing now with anything that has the x. There we go. So x 4a plus b. And then everything else is the constant. So I'm doing the number of lines here. So 3, that one should just have 1. Okay. So now I need 4a plus 2b plus c. This leads us to our system of equations. But it's not too bad. You might think this must be bad. It's not too bad. Because automatically we know that our minus 2 here, this negative 2 in the front, has to be a, because they're next to the x squared, and that's all it can be. So negative 2 must equal a. Boom, we already have our a. That's great. Now, we also know that negative 5 needs to equal 4a plus b. And that's, of course, because this negative 5 or minus 5 is what's in front of the x. So, not sure why I'm doing a lot of lines here. Let's take it down a notch. Let's get rid of that one, that one, that one. There we go. Now, I'm already in blue. No, let's just go back to that. And then our minus 1 here, which will become negative 1, needs to be the rest of everything. All those constants need to be minus 1. It's the only way to make both sides equal. So we can now have minus 1 equals 4a plus 2b plus c. And we can use what we have. So of course, if a has to equal negative 2, then that allows us to do 4 times negative 2 plus b. And we just solve on down, and b must equal 3. So we have a equaling negative 2, b equaling 3, and then we just use what we just found. So 4, and we have negative 2. Feel free to do this on your own. 2 times 3 plus c. Negative 8, 6, c. And it looks like, am I going to make it? C should equal 1. Yay! And so what we just found is our A, B, and C. We're not done. That's not like a point like what we saw in earlier section. But it does tell us the numerators that we need for our partial fraction decomposition. So we know A is negative 2. So I'll have negative 2 over x plus 2 plus b, which is 3, over x plus 2 squared, and then plus c. c is 1 over x plus 2 cubed. The idea, of course, is if you were to add these 3 fractions together, you would get what you see over here on the left-hand side, believe it or not. But again, there are some things where having the decomposition is helpful to us. So that's what we have to learn how to do it. The last thing you're going to see in your notes is kind of just some different cases. And we've seen the majority of these cases, we've seen these cases already, been doing some examples, but it's just a reminder of, if you see any of these situations, this is what the right-hand side should look like. So I just want you to kind of have this as a reference so that depending on what situation you see, you know what the fractions should look like, so that then you can solve for your A, B, C, and so on and so forth. So that is section 10.7.